Here's a graph of the potential energy of an object versus its position, and we're asked to identify all the points of equilibrium. So this relies on the expression force is equal to the negative of the derivative of potential energy with respect to position, which, by the way, follows from these two expressions. Work is the integral of F dot dx. Now, we often say F dot ds, don't we? But if an object is constrained to move only along the x-axis, then it's just as well to say F dot dx. And then we also have the expression work equals negative the change in potential energy. So given those two, it follows this must be correct. Well, the derivative of potential energy with respect to position would be nothing more than the slope of this graph. And equilibrium means where is force equal to 0. So we're just trying to find the places where the slope is 0, and that's clearly at x equals 2 meters, and again at x equals 5 meters. So part A of this problem was easy enough. In part B, we're given that the total energy of the object is 4 joules. So we say capital E equals 4 joules. But we also know that the total energy comes in two different forms, either kinetic or potential, and so the total energy is the sum of those two. As the potential energy goes down, the kinetic energy goes up, and vice versa. So what is the kinetic energy of the particle at x equals 2 meters? So we look at our graph. When x equals 2 meters, the energy, potential energy is 1 joule. So if we rearrange this equation, kinetic energy is the total mechanical energy minus the portion of that total mechanical energy that's potential. So in this case, it's a total energy of 4 joules minus a potential energy of 1 joule. That is for the position x equals 2 meters. So the kinetic energy is 3 joules when x is equal to 2 meters. Now when x is equal to 4 meters, we see that the potential energy has gone up from 1 joule up to 3 joules. So if the potential energy goes up, the kinetic energy must go down so that the total energy remains 4 joules. This is the idea of the law of conservation of energy, right? So now our total energy minus our potential energy gives us our kinetic energy. This is 4 joules minus 3 joules to give 1 joule. 1 joule of kinetic energy when the position is 4 meters. Can the particle reach the position x equals half meter? Well, let's see. There's x equals half meter. And according to our graph, if it were at the position x equals half a meter, then the potential energy would be 6 joules, but that exceeds the total energy of the system. Or in other words, at that point, the kinetic energy would have to be equal to 4 joules minus 6 joules, which would give negative 2 joules, but kinetic energy can never be negative. So the answer is no, and our explanation hopefully is clear. Can the particle reach the position x equals 5 meters? It looks like it. It looks like at x equals 5 meters, the potential energy is just slightly less than 4 joules. So the kinetic energy then would be 4 joules minus, I don't know, maybe we estimate this as 3.9 joules, which would be 0.1 joules. So as long as the kinetic energy has a positive value, then yes, the particle can reach that position. Lastly, given that we have a graph of potential energy versus position, can we plot the graph of force versus position? So one more time, force is negative du dx, or in other words, it's the negative of the slope of the graph of potential energy versus position. So what we need to do is find the slope of 3 line segments. We need to find the slope of this line segment, this line segment, and this line segment. Whatever those slopes are, we'll take the negative of those values, and that'll give us the force. So how about we choose a calculation of rise over run based off of this triangle. So this will give us a slope of 4 joules, right, from 4 up to 8. That's a rise of 4 joules, divided by, that's a run of just 1 meter. Oh, and by the way, a joule is a Newton meter, so a Newton meter divided by a meter gives us newtons. So indeed, force should be the derivative of potential energy with respect to position. Actually, the slope of this segment is equal to negative 4 newtons, which means the force would be equal to positive 4 newtons. Let's find the slope of this line segment. We can look just here. So in calculating that slope, we get positive 1 joule divided by 1 meter, or positive 1 newton, which means the force is negative 1 newton. And this last line segment, let's look here to calculate our slope, our value of rise over run. So here we have a slope equal to negative 2 joules per meter, which means the force is positive 2 newtons. So from 0 almost up to 2 meters, just a little bit short of there, there's a force of positive 4 newtons. And then from just a little beyond x equals 2 meters, up to just slightly before x equals 5 meters, there's a continuous slope or a continuous force of negative 1 newton. So from here to here. And then from x equals just a little beyond 5 meters all the way up to 7, the force is a continuous 2 newtons. Okay, so that leaves the question, in these regions, what's the graph look like? But I think it's easy to argue that we can complete the graph by connecting these points. And there we have it. Thanks for watching.